The transfer of a proton from an acid to a base molecule is one of the simplest reactions which will be discussed in this book. So therefore, it is an excellent reaction to introduce ourselves with the concepts of reaction mechanism and thermochemistry. Reaction mechanism describes in detail how a reaction occurs. Or in other words, it is a step-by-step description of how a chemical reaction takes place. Reaction mechanism will describe which bonds are broken and which ones are formed, and it will also tell us the relative rates of various bond breaking and bond forming steps. A complete mechanism ideally describes the position of all atoms and the energy of the entire system during each and every instant of a reaction. This, however, is rarely ever achieved in practice. Thermochemistry is the study of the energy of entire system at each and every instant of a reaction. The information gained from thermochemistry steps help us to decipher various steps of a reaction mechanism. Before learning more about reaction mechanism and thermochemistry, we must understand why a reaction does take place. So imagine that we have uh, we have an acid such as Ha and a base in a container and along with some solvent. And we have a bunch of acid molecules and base molecules. And within these container, so these are randomly moving. So acid molecules and base molecules are just randomly moving. And when they are moving, they will collide with the walls as well as they will collide with each other. So these collisions happen at random. So all these collisions are random collisions. The velocity at which these molecules collide with each other, so that uh, um, that tells us the kinetic energy of these collisions. So kinetic energy depends on the speed or velocity by which they are moving. So when these molecules collide with the low kinetic energy, nothing really happens. They just bounce off from each other. But as the kinetic energy increases, the molecules will bend, flex, or deform. And that's all because of the additional kinetic energy. A good example of this kind of collision can be understood. Imagine that there is a tree uh, branch. So imagine if this is a tree and there's a tree branch, and a monkey is jumping up and down on this tree branch. So if the jump is not that strong, so the branch will flex a bit, but then it will come back to its original place. But if monkey jumps really high up and then hits the branch will flex a lot and it will completely break off and then it will go. So this is analogous to a bond being broken. So if these collisions are low energy, they just bonds just uh, flex and they come back to their original place. But if the kinetic energy is high enough, then the bonds will break, just like the branch will break. And that's the point when the reaction bonds will break and new bonds will form and the reaction will take place. Now, how kinetic energy can be increased? We know that adding temperature increases the kinetic energy of molecules. So it means if we heat up the system, all these molecules, acid and base molecules, they will start moving faster. Moving faster means that their collisions will have high energy. High energy means then those collisions will be energetically high enough that the bonds will break and new bonds will eventually form and reaction will take place. So the reactions that result by virtue of the kinetic energy put into the reaction vessel due to temperature are known as thermal reactions. So this would be an example of a thermal reaction. So during the collision process, which results in a reaction, a structure is formed which is known as transition state. And this transition state is also commonly called as activated complex. Now, activated complex has a particular geometry possessing partially broken bonds and partially formed bonds. For example, if HA is colliding with B, so if this collision takes place, the activated complex will be such that it will contain a partially broken bond. So after this collision, we know that HA bond is going to break and HB bond will form. Maybe I should write it in the other direction because proton gonna get transferred. Okay, so that makes more sense. So we know that after the collision, so this bond is gonna break and new bond will form between H and B. So that in the transition state or activated complex, we will have a partially broken bond between hydrogen and the A and a partially formed bond between the base and the proton. So this would be known as the activated complex. And after that, of course, A and HB will be the product. We will discuss more about transition state in the next section. Reaction coordinate diagram is a graph showing the energy changes that occur during a chemical reaction. Energy is plotted on the y-axis and reaction progress is plotted on the x-axis. We use reaction coordinate diagrams to show the changes in energy for the molecules involved in a chemical reaction. An example of a reaction coordinate diagram is shown in the next section. Let's review one more time why most chemical reaction takes place. So many of these chemical reactions takes place via collisions, and during collisions the structure of molecule flexes, confer, and the high energy collisions may distort the structure of molecules. During these collisions, the kinetic energy of the reactants is converted into potential energy, which is stored in the chemical structures in the form of structural strain. So in other words, whenever they collide, the structure of the molecule gets strained. This process is analogous to vehicles colliding. So when they collide, their structure also gets a potential strain. During a collision process, which results in a product, a transition state will be formed, and in transition state we will have partially broken bonds and partially formed bonds. So for example, this is a new bond which will form. It's partially formed yet, and this is the old bond which is in process of being broken. And chemists use reaction coordinate diagram to show changes in energy for the molecules involved in chemical reactions. A reaction coordinate diagram for one-step reaction between HA and a base B is shown here. I would like to point out here is that the x-axis is not the time axis. It's not versus time. In fact, the x-axis shows how far the reaction has progressed in terms of structural changes. It does not indicate time. In reaction coordinate diagram, we'll have a progress line which is indicated by this blue line, and on this line we'll have wells. For example, this is a well and this is another well. So wells are the deep valleys on the reaction coordinate diagram. These wells represent stable structures that have a lifetime. For example, in this well we have a stable structure HA and the base B negative, and on this side we have stable structures which are our products. Apart from these two wells, no other place has any well, so therefore nothing can be isolated in any of this reaction progress line. So although there is a transition state, but remember we cannot isolate it because it's not on a well. The species or the reactants and products, they are relatively at lower energy level, and when they collide their energy increases, and this energy is converted into potential energy which is stored in the structure. So that leads to the formation of transition state. So in transition state, old bonds are in process of being broken and new bonds are being formed. Transition state is at the highest energy level of this entire reaction coordinate diagram. Transition states usually last less than 1 picosecond. A pico is 10 to the negative 12. So it is extremely small amount of time. And the transition states are not stable species by any mean. So every point along this reaction coordinate diagram line, which is not the reactant or the products, so all other points along this line represent a chemical structure which has characteristics of both reactants as well as products. So the points which are closer to the reactant side, for example from here to here, so all of these have more characteristics of reactants, and all of these have more characteristics of products. Let me clean this up. So the collisions between the reactants HA and the base B will result in increase in energy of the system, and those collisions which have high enough energy to go all the way up to transition state energy, those collisions will result in formation of product. So therefore, in order for these reactants to form products, they need to gain some amount of energy to go all the way up to activation transition state. So this amount of energy needed for reactants to go all the way up to transition state is known as free energy of activation. So after the activation state is achieved, new bonds will form, resulting in formation of products. Now products are at lower energy level than the reactants, so hence there will be a net release in energy, and this extra amount of energy which will be released during this reaction is known as free energy of reaction. So as we learn from the reaction coordinate diagram, the difference between the energy of reactant, so these are reactant, and the activated complex. So this difference is known as the uh, Gibbs free energy. So this Gibbs free energy of activation, it controls the rate of reaction. If this free energy of activation is extremely high, so chances are that a collision will result in product will be low. So therefore the rate of reaction will be slow. However, in some other case, if this Gibbs free energy of activation is low, or in other words, the activation barrier is low, it will be easily be crossed by most of the collisions. So in this case, the reaction rate will be fast. So Gibbs free energy of activation determines how slow or how fast a reaction uh, will be. So the branch of chemistry which studies the rate of reactions depending on the energy barrier, so that branch is known as kinetics. On the other hand, thermodynamics is the study of the relative energies between any two entities on a reaction coordinate diagram. For example, in this reaction coordinate diagram, the two entities are reactants and products. So the difference between the energies of reactants and products, so this difference is known as change in Gibbs free energy, or simply change in free energy. So Gibbs free energy. And it is denoted by delta G naught. This subscript naught indicates that the reaction was carried out at standard conditions, which means temperature was 298 Kelvin and pressure was 1 atmosphere. The change in Gibbs free energy, or delta G, controls the rate and equilibrium of the reaction. And this Gibbs free energy in a reversible reaction or at equilibrium is given by this expression. So we can calculate delta G naught from the equilibrium constant of a reaction. In this equation, R is a gas constant and T is the temperature in Kelvin. A fundamental principle of nature is that all systems will spontaneously attain a lower energy state if a pathway is available. So if in a process or if in a reaction, if the products are more stable, which means they have lower energy value, then the change in energy is negative. A negative delta G is favorable. So for example, in this reaction, in this energy diagram shown here, the products are at lower energy level. So therefore this reaction will have a negative delta G value. And negative delta G value is favorable, and the process in which or the reaction in which delta G is negative, those kind of processes are known as exergonic reactions or exergonic processes. We should not misunderstand exergonic with endothermic or exothermic. Um, so exothermic reactions are those reactions in which heat is evolved. Delta G is not the heat energy. Delta G, in fact, I will explain in a little while later that it is a combination of the enthalpy, which is delta H, and entropy of the system. Now, if delta G is negative, then the reaction is known as exergonic, and in those reactions in which delta G value is positive, those reactions are known as endergonic reactions. The change in free energy, that is delta G, is a function of enthalpy, which is delta H, and entropy, and it is given by this equation. So in order to calculate the delta G of a reaction, we need to take a look at delta H of that reaction and the change in entropy of a reaction. So not all energy releasing reaction will be spontaneous, because if delta G is negative and they lead to a large negative delta S value, they may still end up non-spontaneous. But those kind of calculations are seen more in general chemistry branch or physical chemistry portion of chemistry. In organic chemistry, we rarely have to calculate all these values. So for now, we will only remember that delta G is the free energy or Gibbs free energy of the system, and in order for system or reaction to be spontaneous, delta G value should be negative. And delta G is calculated by, or is a function of enthalpy as well as entropy. In the beginning of this chapter, we learned how to compare strengths of acids by comparing pKa values. In this section, we will learn how to make such comparisons by analyzing and comparing their structures without the use of pKa value. We can predict the strength of any acid by comparing its molecular structure. The overriding principle in determining the relative acidity of uncharged organic acids is the stability of anion resulting from the loss of proton. So in other words, if we have any organic acid such as AHA, in order to see how strong this acid is, we need to find the stability of the conjugate base, or A negative. So this anion, more stable this anion A negative is, more stronger the acid. So that is the principle behind this entire concept. The factors which affect the stability of this conjugate base are which atom bears the charge, so in this case we will see if the charge is on more electronegative element, it will be more stable. Similarly, if charge is on a larger atom, it will be stable. And then the next factor which affects the stability of this anion A negative is resonance. So if there is a resonance in the structure of A negative, it will be more stable. So having resonance is a positive thing. And so third factor which affects the stability of anion A negative is induction. So induction we can explain having polarity in the bonds. I'll explain induction in detail in few slides later, but for now just remember having induction also stabilizes the anion. And then the last factor which affects the stability of anion is uh, what kind of orbital holds the negative charge. In following slides, we will take a look at all these factors in detail, and I call this concept as ARIO. So it's ARIO. So A stands for atom. So what atom holds the charge? R stands for resonance, I stands for induction, and O stands for orbital. So ARIO is the concept by which we can determine the stability of this anion, and from the stability of anion we can say something about the strength of this acid. So let's discuss the factors affecting the stability of conjugate base in detail. So as I mentioned earlier, I call these factors ARIO, and first we will study the effects of A. A stands for atoms. So under A we have two effects. First one is electronegativity of the element. So let's see how electronegativity affects the stability of the conjugate base. Imagine we have three organic molecules. First one is an alcohol. The second one is an amine, and third one is just a plain alkane. Uh, let me okay, so if these organic molecules donate a proton, the protons which are labeled in blue color, so if they donate these blue colored proton, they will act as an acid, right? So their conjugate base will be so these will be the respective conjugate bases. So now we need to know without the pKa values which one out of these three is stronger acid. The concept we learned previously is we need to look at the stability of these conjugate bases. Whichever conjugate base is more stable, that acid will be stronger acid. So let me rephrase it. Whichever conjugate base is more stable, the acid from where that conjugate base is formed, that acid will be more stronger. Now, so first factor which affects the stability of conjugate base is A, and under A we have electronegativity first. So we need to look at the electronegativity of the element which holds the negative charge. And remember, high electronegativity means high electronegativity of atom holding charge means more stable. So in other words, if the atom which is holding the charge has a high electronegativity, that means that atom likes to have electrons around it. So if it likes to have electron around it, so it means it will be more stable. So in this case, we know that oxygen is high. Oxygen has the highest electronegativity, so it means it's more stable. Nitrogen close behind oxygen, so it will also be relatively stable, but not as stable as oxygen. And carbon does not have high electronegativity, therefore carbon will be highly unstable. So it will be highly unstable. It will be and this one will be most stable. So if number one conjugate base, or the oxygen conjugate base, is the most stable, so therefore this compound will be the strongest acid. I mean, I'm saying strongest, but I'm comparing only these three. Methanol by no mean is the strong acid, but comparing these three, methanol, the first compound, is the strongest. And if this is the most unstable conjugate base, so that means this one is the weakest acid in this bunch. And then the amine would be the intermediate. And to confirm whether our prediction is right or wrong, I'm gonna mention the pKa values of these three substances. So pKa value of alcohol is about 16 approximately. pKa value for amines is approximately 38, and pKa value for alkanes is approximately 51. So pK value now clearly show that alcohol is the strongest acid, and we already predicted it to be the strongest. So that's how we can make our prediction even if pK values are not available to us. The second factor which affects the stability of conjugate base under A is the size of atom. So this factor only comes into picture when we are comparing two acids where the conjugate base has an atom within the same group. So for example, in this case, we have a reaction between two organic compounds in forward direction. The sulfur compound is donating the proton, so therefore sulfur is acid. This compound, this is thiol, is acid. In the reverse reaction, the alcohol or oxygen alcohol, so this is donating the proton, so therefore methanol is acid. And now we need to see which one is stronger, because we need to predict the equilibrium, whether it's a forward or reversible equilibrium. So according to the rule, if the charge is on two atoms which are within the same group, then the atom which has larger size will make that charge more stable. So in other words, the larger the atom bearing the charge, greater is the stability. So this can be seen with the help of this uh, model. As you can see, in case of sulfur, sulfur atom is much larger than the oxygen atom. The pink atom here is oxygen and the golden one is sulfur. So larger atom means that the negative charge is dissipated more better, or in other words, on larger atom the negative charge is delocalized better. So if it's delocalized or dispersed better, it makes the atom which is holding the charge more stable. So therefore the species with negative charge on larger uh, atom is more stable. So in other words, this one is more stable. So more stable means that the acid from where this conjugate base came from, so this one is stronger acid. Therefore, methanol is weaker acid. So if methanol is weaker acid, so this reaction, the equilibrium will be shifted from stronger to weaker, so it will be towards the right. The second factor which affects the stability of conjugate base is resonance. Now, we know that if any species has more resonating contributing structures, it will be more stable. So therefore, in any conjugate base, if the anion has more contributing resonance structure, it will be more stable, which makes the acid from where that conjugate base came from uh, be more stronger. So let's compare acidity of alcohols and carboxylic acids. So for example, if we have an alcohol molecule and alcohol molecule donates a proton, the conjugate base from alcohol will be this alkoxide ion. Now, the negative charge in alkoxide is on oxygen atom, but it does not have any resonance. Oxygen is highly electronegative, so that's good, but it does not have any resonance. Let's write the acid-base reaction in case of a carboxylic acid. For example, acetic acid. So in case of acetic acid, when it donates a proton, the conjugate base of acetic acid is the acetate ion. Now in both cases, the conjugate base, the negative charge is on oxygen atom. So therefore, the atom factor for both cases is the same. So we cannot compare the difference in stability by judging or by looking at the electronegativity of the element. Both are same. So that's why we go to the next factor, which is resonance. We already established that there is no resonance in case of alcohol or conjugate base from alcohol. However, in case of carboxylic acid, it does have a contributing resonance structure, and we can write the resonance in carboxylate ion as shown here. Due to the presence of this resonance, carboxylate ion is more stable. And because carboxylate ion is more stable, hence carboxylic acids are stronger acids compared to alcohol. And the evidence is from the pKa values. The pKa value of carboxylate ions is approximately 4.7, and pKa value of methanol is approximately 16. So from the pK values, we can also conclude, or we know that carboxylic acids are stronger acids. But even if we don't have pK value, we can compare the stability of conjugate bases and predict the relative strength of alcohols versus carboxylic acids. The third factor which affects the stability of conjugate base anion is the inductive effect. Inductive effect is seen in those organic molecules in which a strongly electronegative element is present adjacent to the proton donation site. For example, let's take a look at two acids. So first is regular acetic acid, and then the other compound is a derivative of acetic acid, but instead of all hydrogens, we have now a chlorine atom connected to it. So in both cases, the proton is donated by the carboxyl group. Let me change the color. So in both cases, after it donates the proton, the conjugate base would be so in molecule A, and that's the B. I'm ignoring the hydronium ion. Now, the first two factors, which is the electronegativity of element and resonance, will not help us to distinguish the strength of or relative strength of these acids, because in both cases the negative charge is present on the same element, which is oxygen, and in both cases we have same number of resonating structures. So these first two factors do not come into picture. Now the third factor, induction effect, plays an important role. Now what's the meaning of induction effect or inductive effect? In inductive effect, the presence of a highly electronegative element such as chlorine in this case, so it withdraws or pulls the electron density towards itself. So because chlorine pulls the electron density towards itself, so this will create an inductive effect, because now this carbon will become slightly positive or delta positive. So therefore this delta positive will withdraw some of the electron density towards itself, and eventually this withdrawal of electron density will result that some partial negative charge will also get transferred here. So this can be best visualized by the electron density plots. Those are computer simulation models, and pictures of those are given in the book, and you will see that whenever there is a strongly electronegative element present in the vicinity, so this electronegative element stabilizes some of the negative charge by pulling the electron density towards itself. No such stabilization is present in the uh, acetate ion here. However, the chloroacetate ion, there is a stabilization due to the inductive effect. So this effect is known as inductive effect, and because of this inductive effect, the chloroacetate ion is more stable. So because this one is more stable, so hence the acid from where this conjugate base come from is more acidic or stronger acid. And we can confirm the strength of this acid. The strength of this acid or pKa value is approximately 2.8, and pKa value of acetic acid, we know it's about 4.7. So clearly presence of one chloro atom or chlorine atom in the adjacent covalent bond uh, stabilizes the conjugate base, and hence it makes it stronger. The stabilization by the inductive effect falls off rapidly um, with increasing distance of electronegative atom from the site of negative charge in conjugate base. So we have examples of uh, three different alcohol molecules. In all of these molecules, we have fluorine atoms present in nearby the negative charge. So after this alcohol donates the proton, the negative charge will be on oxygen. So in first example, in this first ethanol or trifluoroethanol, fluorine is only two covalent bonds away. In the second case, fluorine is three covalent bonds away, and in the third one, it's four covalent bonds away. And just for the reference, if we have no fluorine in alcohols, uh, their pK value is approximately about 16, between 15 to 16. So if there is no inductive effect, alcohol pK values are between 15 to 16, just for the reference. So let's compare what effect fluorine brings to the acidity of these molecules. So in first case, where fluorine is quite right next to the OH group, the pKa value is 12. So that's a significant increase in acidity between um, alcohol without the fluorine and with the fluorine. So inductive effect is playing a major role here. So increase of one extra covalent bond between the fluorine and OH, you can see the pK value for increase quite a bit. So it is now 14.6. Still, inductive effect is playing a role a bit, but not that much. And when we have four covalent bonds between the electronegative element fluorine and the OH, now pK value is the same as if there is no electronegative element. So in this case, uh, inductive effect is not playing any role. So in other words, inductive effect only plays a part if the electronegative element is within 3 carbons from the negative charge. More than 3 carbons, it does not play any role. A similar example we can see in case of carboxylic acids also. When there is no halogen or electronegative element present, the pK value is 4.8 approximately, and that's where most carboxylic acid pK value is. Having chlorine 4 carbons away, uh, almost there is no effect. It's almost the same. But if chlorine is 3 carbon away, now the pK value is 3.98, and if it's only 2 carbon away, then pK value is 2.83. So in other words, closer the electronegative element, more uh, stronger effect of inductive effect will be seen, and more stabilization will happen, and hence the acid will be more stronger. The last factor on which the stability of conjugate base anion depends on is the orbital. Uh, so by orbital I mean in what kind of orbital hybridization the atom possess on which there is a negative charge. So let me explain what do I mean by that. So before we look at the hybridization or anything else, let's take a look at the shape difference between s orbital and p orbital. So in the shape of s orbital is a spherical shape and p orbital is a dumbbell shape. So in case of s orbital, the negative charge, if there's an additional negative charge, so the s orbital is homogeneously distributed around the nucleus. So nucleus is somewhere in the center and the negative charge is spherically around the nucleus, so it's more stable. So in other words, the negative charge or if you have additional electron or negative charge, it is more stable in s orbital as compared to p orbital. Okay. Now, in case of organic compounds, we neither have pure S nor pure P. We have hybridization. Okay. So then it depends on what kind of hybridization state do we have. So we have three different kind of hybridization state which are available. So one is sp3, the other one is the second one is sp2, and finally we have sp hybridization. In case of sp3, we have one s and 3p. So it means we have 1 out of 4 orbitals. So one orbital is s and 4 is the total number of orbital. So if you calculate in sp3, 1 out of 4 orbital is s. So therefore it has 25% S character. That's how we measure S character. That how much percentage is S. So 1 out of 4 would mean 25%. In sp2 we have 1 out of 3 is S. So therefore S character is 33%. And finally in sp hybridization we have 1 out of 2 is S. So it's 50% S character. So as I explained here, the negative charge is more stable in s orbital, and now in organic compounds we don't have s, we have sp. So what we look for is the s character. So if the negative charge is present on in in an atom which is sp hybridized, so that atom has 50% S character compared to sp3. So in other words, negative charge will be more stable if it's in the sp hybridization state as compared to sp3. So higher the percentage of S character in the hybrid orbital of the charged atom, more stable will be the anion. So let me explain with the help of an example. So imagine we have three different organic molecules. So one is a simple alkane, the other one is alkene, and the third one is alkyne. If they donate proton in alkane, the resulting conjugate base anion will be this one. In case of alkene, the conjugate base anion would be this one, and in alkyne the conjugate base anion would be this one. In all three cases, the negative charge is on carbon atom. Now electronegativity is same, size is same, there is no resonance, there is no induction, so therefore the first three component of ARIO equation does not distinguish the acidic character of any of these three compounds. That's where the final part or orbital part comes in play. So now we need to look at what orbital or what is the hybridization state of atom where the negative charge is. In alkanes, we know the hybridization is sp3. In alkenes, we have hybridization sp2. So this is sp3, this carbon is sp2, and in alkynes, we know it's sp character. So greater S character means more stable. So therefore, alkyne anions are more stable compared to the other two, and this one is the least stable. So alkane anion is the least stable. So therefore, the more stable the anion, more stronger will be the acid. Hence, alkynes are the most stronger acid in this group. By no mean alkyne is an acid, but in comparison to alkanes and alkenes, alkynes are the stronger one, and the alkane is the weakest acid. And this result is evident from the pKa value. So alkane pK value is 51 approximately, and alkyne pKa value is approximately 25. That's a huge difference. I'm not sure if you can comprehend the difference. This, according to these number, alkynes are trillion times, billion times stronger than alkane, the acidity, and alkenes are in the middle of those two. In case of alkene, the pKa value is approximately 44. So alkenes are stronger than alkanes, and alkynes are the strongest acid, and we can identify the acid character with the help of hybridization. Let's summarize all the principles we learned in previous section. So in previous section, we learned how to compare the acid strength of organic molecules without referring to pKa values. The principle or the guiding principle behind this concept is that we determine the stability of the anion resulting from the loss of proton. And more stable the anion is, the greater will be the acidity of the acid. So in summary, there are 5 factors. So first factor was the negative charge on more electronegative atoms. So if negative charge is more on more electronegative atom, the anion will be more stable, hence the acid will be more stronger. Second one was the negative charge on larger atom. Larger atom makes the negative charge more stable, hence the parent acid from where that anion is formed will be stronger. Next one, so these two, I'm calling these two as atom effect, so A. Next one is the resonance. If there is resonance in the anion, that anion will be stable, and hence the acid from where the anion is formed will be more stronger. And the third effect is the inductive effect. Having a strongly electronegative element in covalent bond adjacent to the atom where negative charge is will make that anion more stable. So this effect is called inductive effect, and the acid from where the anion is formed will be more stronger. And finally, we have orbital, so I'm calling it O. So having the negative charge in an orbital with more S character makes that anion more stable, and hence the acid will be more stronger. One thing I would like to mention that there is a hierarchy in these effects. For example, if we have two contradicting effects, we always go with the first one. So if atom is deciding that one acid is stronger than the other, we do not need to look at the remaining one. We call our result at the first step. So in other words, we always look for atom first. If we can decide the acid strength, then that's good. If not, then only we move on to the next step, which would be resonance. And if we can figure out with the help of resonance, then good. Then we don't need to look at the remaining ones. Those are unnecessary. And if resonance is unable to decide, then we go for inductive, and if inductive is unable to decide, then we go for orbital. We never start from this side. We never start from orbital first and then go for the other uh, effects. So always start from atom, then go to resonance, then go to inductive effect, and finally orbital. The third definition of acids and bases was given by Gilbert Lewis, the same scientist who proposed the Lewis dot structures. This is the same guy. The Lewis definition of acids and bases is broader than the Bronsted and Lowry definition. According to Lewis' definition, acidity and basicity are described in terms of electrons rather than protons. A Lewis acid is any molecule of ion that can form a new covalent bond by accepting a pair of electrons. So in Lewis' definition, acids are electron acceptors, and Lewis bases are those molecules which can form a new covalent bond by donating a pair of electrons. According to Lewis, the bases are electron donor. So it's opposite, kind of opposite of Bronsted and Lowry definition. Now, why this definition was proposed? It was proposed because Bronsted and Lowry was unable to include some acids and bases. For example, aluminum chloride in organic reactions, this compound act as an acid. Similarly, BF3 is another example of a compound which is an acid, but according to Bronsted and Lowry definition, they don't have protons to donate, so that's why they cannot be included in the definition of Bronsted and Lowry acids and bases. So to include these kind of substances, Lewis proposed definition of acid and base is based on electron acceptors and electron donors. So a general reaction of Lewis acid and Lewis base reaction is given here. So if a base is donating a pair of electron and A is accepting, so therefore A is a Lewis acid and B is a Lewis base. This donation of electron will result in a new covalent bond formation. The examples of Lewis acid and bases are given here. So in this reaction, bromide ion is donating a pair of electrons to form a new covalent bond. Therefore, bromide is a Lewis base because it is donating, and this butyl cation, it is a Lewis acid because it's accepting a pair of electrons to make a new covalent bond. As I mentioned in previous slide, BF3 is another famous example. So boron trifluoride is a Lewis acid because it's accepting a pair of electrons from this ether. And because ether oxygen is donating the pair of electrons to make a new bond, so therefore oxygen or this ether is acting as a Lewis base. Let's take a look at a few of reactions in which we have Lewis acid and Lewis base pair, and we need to label which of the following compounds are Lewis acid and which one is Lewis base. Let's solve one by one. Now, because Lewis' definition of acid and base depends on electrons, therefore it's important to draw the complete octets with lone pairs of all the atoms given in the reaction. So remember, according to Lewis definition, acids are electron acceptors. Actually, it should be electron pair acceptors. And bases are electron pair donors. Okay, so before we assign which one is an acid, which one is a base, let's complete the Lewis dot structure of these compounds. So we know that chlorine has 3 lone pairs to complete its octet. So same way, these 3 chlorines will also have 3 lone pairs. Before we assign which compound is Lewis acid and base, we must find an atom or a species which is electron deficient. That will help us a lot. If we look at this whole thing, so all the atoms in this uh, alkyl halide have a completely full octets. However, if we look at aluminum, you will see aluminum has only 6 valence electrons around it because it's forming 3 covalent bonds or 3 bonds, so therefore it has only 6 valence electrons around it. So at this point, aluminum is electron deficient. Therefore, aluminum is a prime candidate to accept a lone pair of electron, and that's what it does. So if aluminum wants to accept a lone pair of electron, that has to come from another neighboring molecule. So neighboring molecule is this alkyl halide, and in this alkyl halide only chlorine has extra lone pair of electrons to donate. So this reaction will go like that. So chlorine will donate 1 uh, electron pair to aluminum, and in doing so aluminum will gain 2 electrons and its octet will be complete. And because chlorine has lost its lone pair, therefore chlorine will get a positive charge and aluminum will get a negative charge because it has gained 1 extra electron. Okay, so now we know aluminum is the acceptor, so aluminum is the Lewis acid and alkyl halide is the electron pair donor. So this alkyl halide is a Lewis base. Okay, similarly, let's complete the octets first. So in example B, oxygen was missing lone pairs. Now this is really easy because in this case we already know carbon cation or carbocation does not have its octet complete and it does have a positive charge. So that's where the reaction's gonna take place. So oxygen lone pair will be donated to carbon. Now because water is donating the pair of electron, it's a donor, so therefore water is a Lewis uh, base because the donor is the base. On the other hand, this carbocation, because it's accepting it, so this will be Lewis acid and the end product will be this one. Now, because oxygen lost a pair of electrons, therefore oxygen gets a positive charge, and carbon gained an electron. Therefore, the formal charge or the positive charge on carbon got neutralized. So, in example C, we have another carbocation and it's reacting with bromide ion. So bromide ion, we know it has 4 lone pair of electrons. So in this case, the electron will be donated from the bromide. So because bromide is donating the electron, so therefore bromide is a Lewis base, and carbocation, because it's accepting the pair of electrons, so it is a Lewis acid, and the end product will be the one in which there will be a new bond formed between carbon and bromide, because bromide donated the electron. Therefore the negative charge of bromide got neutralized, and the positive charge of carbon also got neutralized. So end product will be a neutral species. And finally, in the last example, so we have oxygen. Oxygen is the one who's going to donate the electron pair. So, and we will follow the rules of mechanism. The base of the arrow, curved arrow, always starts from the pair of electron, or the arrow represents the movement of the electron pair. It does not indicate the movement of atoms. Uh, so in, in this case, the end product will be now, because this alcohol molecule is donating electron pair, so this will be a Lewis base, and carbocation will be Lewis acid. In all these examples, we saw that many of these organic molecules, they do not fit the definition proposed by Bronsted and Lowry. For example, bromide ion, it cannot be a base according to Bronsted and Lowry, because it's not accepting a proton. So that's why the Lewis definition of acid and bases were proposed, and this definition is also used quite a bit in many organic reactions. Okay, with that, we conclude chapter number 4. In this chapter, we learned about acids and bases, and we discussed different definitions of acids and bases. And as I mentioned, the most common definition which we will use in this course is Bronsted and Lowry definition. We learned about how to calculate the strength of acid using pKa values, and we also discussed what is the meaning of equilibrium between an acid-base reaction, and how we can predict the direction of equilibrium by looking at the strength of the acids. We also briefly learned about the thermochemistry portion of acid-base reactions, and what's the meaning of the acid-base reaction in terms of collisions, and how we can qualitatively compare acid strength of two organic molecules by looking at its molecular structure. And finally, we briefly discussed about what are Lewis acids and Lewis bases. Thank you everyone for watching this video. If you have any question, please contact me, and have a wonderful rest of the day. Bye bye.